So hello, everybody. It's me again. We are going to talk now about a different topic, as Will was introducing. We're going to try to understand why it's important and how can we make AI more transparent. So, and I want to start with this slide. This is a cover of a magazine that says, our machines now have knowledge we will never understand, alien knowledge. So this is public perception. There is people that sometimes is not necessarily in this field, people that are users of AI that are exposed to this type of perception. At the left, you see a paragraph that says models that are often beyond human comprehension. And I want to start this talk saying that this is not a black box. And as an anecdote, so several years ago, the first time I listened the term black box, I probably was very naive, and I couldn't understand why people was calling this a black box. And in my mind as a researcher, not as a human being member of a community, but as a researcher, I was saying, for me, this is clear. It's clear. I know exactly what is the architecture I'm using. I know exactly why we chose each one of the layers that I have in there. I also can dissect this neural network and see each mathematical operation that is happening. And in some cases, I even can take like snapshots of what neurons, well, in all cases, I can see what neurons are activated in each one of the layers. I also understand that if I work with convolutional neural networks, I can capture features that goes from low-level features to high-level features, depending on which layer I'm looking at. So for me, as a researcher, this wasn't a black box, and it still isn't. So at the same time, I was trying to understand, okay, what people is talking about. And one day I understood that the problem with this is that people do not necessarily trust on AI. And it's like in real life. If somebody that you trust tells you, we need to travel to this place, you're probably going to say, okay, let's go. But if somebody that is new, that you don't trust enough, tells you exactly the same, you're going to ask for an explanation. So humans, us as humans, we are very used to get explanations when a decision is taken. So it's not that the machine learning is a black box, it's that humans get explanations in a different way, understand things in a different way. And you can do this loosely comparison with your brain. You don't know, as a human, you don't know which are the synapses that are activated, or what neurons or what part of your brain is used for different tasks. But if your brain is basically identifying a cat, you can ask to yourself why I'm saying that this is a cat, and you're going to say, because it has whiskers and long tail and pointy ears. So we can do explanations. So explanations are related with trustability. So we need to trust on these machines. So, and why this trust? Because we have been doing software for years, and everybody trusts software. Software is able to control airplanes, and everybody here has traveled in an airplane. That's kind of a scary scene if you think in a rational way about that. So, but what is the difference? The difference now is that I can create these algorithms. This can be a neural network, the architecture of my neural network, or it can be a more classical machine learning algorithm. But that algorithm by itself, I cannot tell you exactly how it's going to behave, because a machine learning model is the architecture that I have crafted and the data that I'm using to train it. And no matter what type of learning I'm doing, no matter if it's supervised learning, where I'm giving the training data with the labels, or unsupervised, when I only give the training data and expect the system to find patterns, or even if it's reinforcement learning, when I try to optimize a policy for an agent, and I'm giving some kind of function for the reward function. So no matter which is the case, there is data that comes from humans. So now, this is why we need interpretability. We need interpretability, or we need more transparency, because it's not enough. I have read people say, oh, we need to audit the code. Audit the code when it comes to machine learning is not an option. It's not going to give you enough data. So why do we need interpretability? One thing is trust, but there are other reasons. Let me see. OK, another reason is knowledge. So, and there is this paper that was published like 20 years ago when it was a group of medical doctors, and they were studying the risk of mortality from pneumonia. And one of the findings, they had an interpretable model, and with that interpretable model, I think that it was probably a decision tree, they found that asthma patients, asthma is a disease, a respiratory disease, asthma patients have less risk to die from pneumonia than people that is healthier. So, and that was something that you say, so all the medical doctors involved say, no, this is wrong, this is impossible. So what was discovered, and this is how we can discover knowledge, what was discovered is, okay, but the data is saying that. If the data is saying that, there is something here. So what was discovered is that asthma patients, when they get the first symptoms of pneumonia, they go to the hospital. As they go to the hospital earlier, and they also have a history on respiratory diseases, they get treatment early. So the real variable that was important there was time to treatment. Time to treatment wasn't a variable in there. So nobody knew that time to treatment was so critical for this. But now, through this interpretable system, the knowledge has been generated, and now people know, okay, if you have pneumonia, go from the first symptoms to the hospital and make sure that you get treatment early. So the second thing we already were talking about, trust and safety. So machine learning, all the idea of machine learning is to be able to generalize. So you give some training data, and from this training data, the system should perform well in unseen cases. And most of the time we say, and we had a great talk from Professor Benjo this morning, most of the time our hypothesis is the distribution of our training data needs to be exactly the same distribution that our test data, that should also be the same distribution that the data that we're going to have in the real life. It's very difficult to make sure that you are taking into account every use case. How much training data is needed to really make sure that you are taking into account all the use cases in real life? But if you have interpretable models, you can get explanations on what the machine is looking at when they take the decisions. And that gives a little bit more confidence in terms of, okay, when a new case comes, it's going to look at the right place. The next point that is very important, especially for people who really wants to deploy these systems in production, is legal and approvals. There is a lot of industries that are highly regulated. Even for industries that are not highly regulated, right now there are laws. Europe already started with GDPR. GDPR probably is coming, or similar laws are coming everywhere, where the human has the right to ask why a decision has been taken when the decision was taken by a machine. So if a machine is taking a decision that can affect me, I have the right to ask why the machine took that decision. And the last point, but is the last here, but it's not the less important, in fact, it's the more important, is ethics. Sometimes you deploy systems, and these systems have biases on it. Because remember, we say that the machine learning model is the data and the model. So what happens if my training data was biased? I'm going to put something in the market that might discriminate a particular group. So this is something that we want to avoid. So ethics is very important, and not only in terms of bias, fairness, or even things like, imagine you're doing a marketing campaign for a very sweet and highly caloric chocolate. Okay, everybody loves chocolate, So, and you have this chocolate that is really, really, really bad for people who want to lose weight. But your machine, you enter the data from everybody, and what you discover is that the people that is more likely to click on that advertisement is people that is also clicking in the advertisement to lose weight, or people who is clicking in things related with diabetes. But you know that these people is the people who has a higher trend on buying your chocolate. So if you don't have interpretability, you are going to deploy that model, and it's going to target that particular group. If you have interpretability, you might still do it. But now you are accountable, and you know what you're doing. So the point here is a decision that at the end of the day is a decision of the company if you really want to target a sensitive group. So this is why we need interpretability. Now, why we don't have interpretability everywhere? Because if I'm telling you that interpretability is so great, so why I don't have it? So the reason why deep learning in particular is so powerful is because the models are very complex. These models has hundreds of thousands of variables associated with them. And as the model gets more complex, it is more sensitive, more precise. You are able to get better results that are less generic and more accurate for a particular use case. So now, the more complex the project, the algorithm, more difficult is to interpret. So the algorithms that are interpretable are mainly linear models that are pretty easy, that requires lower amount of variables. So there is a trade-off. As everybody says, there is no free lunch. So what can we do? So how can we make a model interpretable? And there are three basic ways here. First one is analyzing the data. Second one is choose a model intrinsically interpretable. And the third one is post hoc systems. And we're going to go through each one of them very quickly, and we can talk later in detail. But analyzing data. What means analyzing data? So analyzing data means I'm going to choose the model I want. I don't care, okay, if it's a super deep learning model or a linear model, but what I'm going to make sure is that I can analyze the data, and after analyzing these results, I can find an explanation. Me as a human seeing the data, I find an explanation. Now, these complex models have multiple variables. So one of the things the techniques that exist for this is, for example, we can use PCA to reduce the dimensionality. Or we can use things like TSNE to be able to project multi-dimensions in 2 dimensions. So in this graph here, basically to show you that this can work for not only for structured data, but also for unstructured data, what we have here is a result. We have 10,000 images of models with clothing. And we wanted to make sure that the machine, we pass that through an ensemble of 3 different very deep neural networks, like ResNet 50, GoogleNet. And now we get a feature vector. This is not interpretable at all. But we want to make sure that that machine is capturing the essence. And the essence ones try to understand what kind of clothing is wearing that model. We didn't want the system to be capturing what is the model pose. We didn't want the system to be capturing the color of the hair of the model. We want the system to be able to capture the clothing. So when you are able to take the feature vector generated by this ensemble of neural networks and project that using TSNE in this space, you can see clusters, and you can say, OK, yes, this seems right. Seems that the same type of clothing is clusterized in different places. OK? So this is analyzing the data. Another thing, and these are if you are in an industry that is highly regulated and you have no other option, you need to go with intrinsically interpretable models. The problem with that is the trade-off with accuracy. Probably you need simpler problems, or you are going to need to sacrifice accuracy. And in this case, I put 4 cases there. You have decision trees. Decision trees allow you to go non-linear, non-monotonic. Decision trees get very complex if the graph gets very deep, so lose interpretability there. Linear models, well, those are good to capture general features, but not specificity. Rule-based approach, so a lot of basically Boolean expressions, or monotonic models that can work in nonlinear cases, but you know that you take one of the independent variables, and you know that when you change that variable, the system is going to always move in the same direction. Now, the more interesting ones are the post hoc systems. Post hoc systems is what we like to research. And what that means that you still use, you're model agnostic, you use the model that is going to give you the best accuracy. And now, instead of sacrificing accuracy, you're going to sacrifice a little bit in the depth of the explanation. So you're going to get high accuracy, but approximate explanations. And I'm putting here 4 different cases that we can do. We can do causal inference to understand what is the cause and effect of different variables in the values that has been inferred by the machine. You can use what is called surrogates or interpreters. So in the case of surrogates, what you do is you have your model. Imagine it's a deep neural network with 300 layers, and at the end, you get your result, your inference. So now you're going to take the input at the output, and you're going to train something like a decision tree, or you're going to train some kind of linear model. And from there, you're going to try to understand what is the complex mechanism that happen inside the neural network. So when you do the decision tree, it's going to tell you an approximative idea of how the neural network is thinking. The third case, and is I think one of the most promising, is LIME. LIME stands for Local Interpretable Model Agnostic Explanations. And family, because now there has been LIME. I think that the original paper was 3 years ago. And this has been a lot of different papers after that. So all the theory here is, OK, the model is complex. The surface of all the possible answers for all the possible observations is very complex. Now, if I look only to one observation and the locality around that observation, I might have something that is monotonic or more linear that can explain that in the locality. So now I don't have an interpretation of why this happened for all my samples. But I can tell you that for this particular sample that I'm looking at this particular moment, the explanation of the inference that I'm doing is this. The last case I was to mention here is sharply values. Sharply values is, that's a term that comes from game theory. And basically, what you do is all the features that you have as input for your model, that can be a neural network or another model, are going now to be players. And the inference is the payoff. So now what you do is that sharply value is a way to calculate how much each one of these players have influenced this payload that I have at the end. So basically what I get is which are the features that have higher influence in the decision that has been taken by the machine. So this is, I think, that where we should be moving. We should be moving towards getting better and better explanations on models that has proven to be accurate. So a couple more slides only to say that truthworthiness is more than only interpretability. Keep an eye on your data. You need to analyze not only the data to see if it's balanced, if there is bias. Also, you need to analyze things like, is this data stationary or non-stationary? What will be the consequence if there is a change on my data? All these need to be analyzed when you do a project. Can I test how trustworthy is a model? The best way after having explanations is do things like sensitive analysis to see if really, if I change a small thing, if I still get the same result. Last slide here is when should I care? So obviously, especially for people who is in enterprises, do interpretability or try to do this extra step implies more work, more time. So when should I care? The first answer is always. I should always care. Now, it's different if I'm creating a mobile application that is going to randomly put or recommend a joke to a user versus if I'm doing a system that is going to be able to diagnose a particular disease. So there is a document called the Algorithmic Impact Assessment. Different countries have already published different versions. This is the one from the Canadian government. So Algorithmic Impact Assessment, what it measures is how impactful in human life is the decision that is made by the machine. And gives you 4 risk levels. Depending on the risk level, you should really do more or less. Bias in the data, you should always do. Interpretability, maybe when the risk is level 3 or level 4. That depends on what you decide. So my key takeaways are regulations. This industry should be regulated. And I'm a researcher, and you might think, why is she saying that we need to regulate this? It's better if we can do whatever we want. But the problem is that if we put regulations, the people who is doing the things in the good way, as everybody in this room, is going to not be impacted, is going to get benefits on that. But the people who is trying to use that in a non-ethical way is going to be punished. The risk here is that if people do things in a non-ethical way, we can continue to stop the industry from advance. So it's important that regulators really start legislating here. And the second thing is, while regulators do that, also at the Stradigi AI, we have an ethics committee. Every single project that we do, we pass it through the ethics committee. And we pass the algorithmic impact assessment. So my recommendation is everybody who is going to do an AI project, think about these things, do the exercise on the algorithmic impact assessment, and decide what you should do to make your algorithm interpretable, trustable, and transparent. And that's it. Thank you.